CIRCA research webinar series. So I am Dr. Yaprak, Onat, Assistant Director of Research at CIRCA, and I'm happy to welcome you. Actually the flooding week, the last presentation that we had with Dr. Leo on Friday started talking about the nearshore modeling of the flooding. And today we have another flooding, actually very fitting for the day. It's about the extreme precipitation and riverine flood risk analysis for the Resilient Connecticut project. I have with me Dr. Xinyi Shen from the Department of Civil Engineering and Environmental Engineering. Dr. Shen's research interests include human disasters and built environment, flood inundation, numerical modeling, remote sensing retrieval, machine learning, hydroecology, and microwave remote sensing. Without further ado, Dr. Shen, the floor is yours.
Thank you, Yaprak, for the introduction. By the way, hello everybody, can you hear me?
Yes, we can hear you.
Great, thank you. So it's my pleasure to share to report the project result to you. This project is primarily done by my student Kang He. So in this project, we have two primary objectives. One is to understand the compound flood impact and identify the coastal area which could be affected by either riverine flood, storm surge, or both type of flood, which we call compound flood events. The second objective is to estimate the land use change impact on the intensity of flood damages, increase of the flood damages. So here's our modeling structure. We basically couple one distributed hydrological model and one 2D hydraulic model. The distributed hydrological model, which is the CREST model, consists of a land surface processes module, runoff, or we can say the rainfall runoff generation module, and a fully distributed routing module. It takes high resolution weather variable fields, including precipitation, pressure, wind speed, air temperature, humidity, radiation, and also remotely sensed leaf area index as the forcing data. And it also takes into account high resolution topographic data, the distributed soil properties, and the land use. Then it outputs the evapotranspiration, the soil moisture and also the graded runoff as the water cycle components. Eventually, we use with the routing module, it computes the river discharge in channels. The parameters of the routing can also be optimized against the USGS observed stream flows. Then we use the stream flow as the upstream boundary conditions and the coastal water level measured by NOAA as the downstream boundary conditions. The coastal water level includes tide surge and mean sea level. We run the HEC-RAS model to generate the inundated area and water depth map. So the CREST model has the fully decoupled water and energy balances, which is quite important for high latitude areas because it contains snow melting caused spring flood. So it's critical for areas like the Connecticut state. And we have a distributed runoff generation and the routing process. We run the model at a high temporal resolution, which is hourly for the entire 40 years. And at a higher spatial resolution, the land surface uses a 500-meter resolution, while the routing uses about 30-meter resolution in order to account for the discharge in small rivers. The model also implements the parallel computation and vectorization for efficiency. The HEC-RAS model can account for two-dimensional unsteady flow, which is usually the case during flooding. And it also parameterize the hydraulic properties. It also implements parallel computation and finally can generate flood mapping, including the flood depth and flood extent. We use a variable resolution from 1 meter to 30 meter for HEC-RAS because for some areas with less topography, we can use the coarse resolution to save computation. For areas like the banking area, which has a contrasting topography, we can use up to 1 meter resolution. And the temporal resolution is 1 minute. Before we apply the model to evaluate the flood impact, we need to validate the model thoroughly as our first step. We validated CREST model in our previous publications in the Kankakee River in Illinois, in Tar River in North Carolina, and many other rivers. And we also validate the CREST model in major rivers in this study area, like the Connecticut River Basin, which we obtained a national coefficient of 0.6. We captured, and in the Oceanic River, which we obtained also a high accuracy. And we successfully captured the major flood, which is in 2005, caused by Tropical Storm Tammy. And the second is to validate the HEC-RAS modeling. It's difficult to obtain a flood extent reference in a small state such as the Connecticut, but we fortunately to have the USGS high water marks, which is the flood depth measured posterior to the events. So the USGS utilized some traces left by the flood and then measure the location and the depth. In the red triangle, we marked several USGS high water marks during Hurricane Sunday, and then we compare our final depth result with the USGS high water marks, because there could be some location error of taking the measurement, taking the observation. So it's safer for us to choose a 10 by 10 meter square around the USGS high water mark, so which gives us 100 pixels as our simulation. So each bar represents this 100 pixels, the distribution of these 100 pixels. If we compare the mean value versus the USGS, the median value versus USGS high water marks, we can finally obtain a mean square error below 0.5 meters. You may notice that for some area, the depth spans quite a large range. This is because in 10 by 10 square, in this 10 by 10 square, it's possible for you to cover some pixels inside of the channel, which gives you a much deeper, much larger depth. Now this is after successfully validating the model, we can safely apply this modeling framework to our study area, which include those polygons in this map. We select the two streamflow outputs here. One is the Farm River State Park, and the other is the Housatonic River of the streamflow. So in order to demonstrate the impact by extreme flood events, we study this New Haven region because it contains both coastal regions and some deep inland rivers. So here's the flood event caused by Hurricane Irene in 2011. So this blue line is our upstream boundary condition output by the CREST hydrological model, and this orange line is the downstream boundary condition of the coastal water level. And as we can see, the high flow or the river flood has strongly overlapping with the coastal water level, represented by this orange line. So this is the animation of the flood inundation dynamics during the Hurricane Irene. And we can see, if we assume that there is no river flooding, which means we use the base flow to represent the river flow, we want to know how much inundation can caused solely by storm surge. And here, and the red bottom figure represents the maximum inundation extent caused by surge only. And we can see it's significantly smaller than the max flood caused by the compound flooding. This is because Hurricane Irene brings heavy precipitation. And this also tells us it's very important to consider both the Riverine flood and the storm surge flood in a compound flood event. So the second case is the flood inundation caused by Hurricane Sandy. And as we can see, if we compare the compound flood result, which is the last figure, the bottom left figure, versus against the inundation extent caused by surge only, we don't see significant difference. The only difference occurs in this area, which is very deep inland, caused by river flow, and this area. This is because Hurricane Sandy brings a lot of very strong wind, which causes strong surge, but it doesn't bring much precipitation. However, if we compare the maximum extent caused by three mechanisms, which is just flow only, flow and surge. I'm sorry, just the surge and tide with just base flow, and both the river flood and the surge and tide. Then we can find that still we have a lot of red area, which is the external inundation area if we consider the compound flood. And here's another, here's some detailed demonstration of those different flood mechanisms. Next, we want to know, so now we know some, we show some examples of extreme cases, but we also want to know the risk. In order to evaluate the risk, we select a river deep inland, which is the Quinnipiac River. According to the pressure sensors data, it's not much affected by the tide, which means it could not much be affected by the storm surge. And here's the stream flow examples. So this area will only be affected by river flow, we assume. So here are the stream flow of both the downstream cross-section and the upstream cross-section as our downstream boundary and upstream boundary conditions. We select the 8 top flood events as circled here to further simulate, to further run hydraulic simulations. But we also want to know what is the mean flood impact it can cause. So we compute the mean flood peak value, flow peak value, using all 40 years data. And then select the flood event, which is closest to that mean value, which is in 2003. It's about 400 cubic meter per second. So here's our the inundation of the 8 flood events, plus these mean events as the last figure. Because this 8 events is significantly higher than this mean event, so we can see even the smallest event has a significant larger flood extent and higher flood depth. And it's very interesting to see the ranking first flood event has a significantly lower flood depth than the second event. The first event is the 2001 event, the Hurricane Irene caused one, and compared to the 2005, it has a higher peak. However, if we compare the flow volume, we can see that the 2005 flood events has a multi-peak rising power, which means a significant larger flood volume. That is why it caused indeed significantly larger flood inundated area and inundation depth. So the second objective is to evaluate the land cover change, which is primarily the urbanization impact on flood intensity. So in order to do so, we need to have some great contrast between the past urbanization and the future urbanization and the current urbanization. However, the USGS NLCD data, in the beginning we want to use the USGS NLCD land cover data. However, when I asked them about the result of 1992, they told me that the USGS person told me that the definition of the classification is different between 1992 and the present. So you cannot compare the imperviousness in the past and now. So that we use another data set which is generated by the Tsinghua University, and they use the machine learning method to finally identify the imperviousness. So imperviousness actually means for each grid, there could be some impervious area like the concrete, which rainfall cannot penetrate to the soil. So the larger impervious ratio, it means it could give you a larger fast flow. So it's of a higher risk of flooding. So in this Quinnipiac River, we can see for some area, if we compare the 2018's imperviousness with the 1985, we can see some area has a close to 100% of the change. Well, if we look at the whole connected river basin, we can see along the large cities, there's some large change of the imperviousness. It means a clear sign of city expansion. So here's the simulation result. These two terms refers to the surface excess water and the subsurface excess water. We can see with increased urbanization or increased imperviousness, we find significantly larger surface excess water, well, less subsurface excess water. And then we also provide the change of those variables. So eventually, we expect a high flow during flood events. And here's a percentage of the change. So if we just select one event, which is the 1980s event, to create this hypothetical scenario, we can find in the 2018's flood event, we have a significantly higher flow peak with a much faster rising period, and a much slower and much faster recession period. So which means the flood is formed much faster than the 1980s urbanization. Well, it recesses also much faster. But since the main damage is caused during the rising to the peak period, so we consider this 2018 flood event, hypothetical flood event, could be more impactful and has a higher intensity than the 1980 flood event. And then we compare the inundation extent and depth. We also observe that the 2018 flood events is more powerful than the 1985 flood event, and it gives us larger inundation area. So in conclusion, we recommend that flood management should consider both the urbanization and the flood and climate change. And we also recommend the modeling of the hydraulic modeling in marsh areas and in high resolution, which can provide detailed inland and coastal flood mapping result. We recommend the parameterization for hydraulic simulation of especially compound events during extreme hurricanes to support flood planning and management. Thank you very much.
Thank you very much for the presentation, Dr. Shen. Just to remind our attendees that you can type into the chat box or like a Q&A box for your questions, and then we're going to try to answer that in general team. So while the questions are coming, we actually have like a couple. The first team is that are you using the Yukon Clear impervious surface GIS maps for the analysis? Why or why not?
I didn't hear the question very clearly, but I think it's about the impervious ratio I'm using, right?
Yeah. So are you using the Yukon Clear's impervious surface layers?
Oh no, I'm using so for the land use, I'm using Clear, but for the impervious ratio, because I'm trying to compare the urbanization between 2018 and 1980s. So the USGS data Yukon Clear data doesn't span so long to that time. So I didn't use that. I'm using this the land cover. I'm using the impervious ratio specifically from this paper.
Mm-hmm. considering your tests between the flow rate and then the compound flooding, in which regions do you suggest that the compound flooding is effective and which regions are not? What would be the distinguishing factor would be for that?
Okay, that's a good question first. And first of all, I want to emphasize sometimes it might not be so clever to tell which region is could be affected by the compound flood, because as you can see from these two events, the first one is the Riverine events in the same area. This show like almost all this New Haven area except very upstream, very inland, could be all this coastal area could be affected by compound flood. Well, in this Hurricane Sandy, because Sandy didn't bring so much precipitation, it doesn't affect much. I mean, considering the compound flood doesn't really affect much. But in general, if you want to make it so in general, I don't think using one or two events can give you a conclusion that which area is affected by compound flood or affected by each one single source. But if you run like over 40 years of events, you might get a better idea. If you want to make a general conclusion, definitely the closer to the upstream, to the deeper to the inland, the closer to the river, it could be less impacted by the storm surge. Well, closer to the coast, you get a high chance of storm surge inundation. But that's a very general recommendation. As you can see, even for this very small Sandy, very light precipitation event of the Hurricane Sandy, you can still see some compound flood, extra area impacted by compound flood. So my recommendation is that you should always be cautious, and if possible, we should always consider compound flood. Okay.
Thank you. Your comparison in the model about like the impervious surfaces, to explain the urbanization approach, can this be also proposed locations for removal for impervious cover for open space or green infrastructure? What are the implications basically like you are seeing from your research results with this land use comparison?
Sorry, what's the first question? The second I hear it clearly.
No, this is like the same thing. It's about like the whole land use change model that you did for the comparison. Can this urbanization modeling approach be used to propose locations for removing of the impervious cover, like so that people can do more open spaces or green infrastructure? What would be the implications of your results?
Yes, it can be. It can be. So if there is some restoration of the forest, of the vegetation area, we can definitely use this approach to resimulate what will be the reduction of the flood risk, flood intensity, after a certain procedure is adopted. So the general recommendation in this work is that you can see the maybe this one is better. You can see that with the increase of the impervious ratio, we have significant deeper of the rising and a higher flood peak and a larger inundation. Yeah, that's it.
This is about your results about the New Haven compound flooding versus the river flooding comparisons. So the questions are generally, what is the magnitude of the water depth in the compound flooding model comparisons?
The inundation depth, it definitely depends on different events. So if we take if we take the Hurricane Irene as a comparison, we can see the depth. It can basically change from about this. I think this color is about 3 meters to 5 meters for this area. But for overland areas, it can change from zero depth inundation to about 3 meters, 3 meters inundation. So that's the impact of compound inundation. If we just that's a comparison between if we just consider the storm surge, because this area is a coastal area, and for many maps, such as the FEMA flood map, they might use just the storm surge to consider the inundation. So if we just use the storm surge and versus we use the compound flood, we might observe about 3-meter inundation in some areas. And even in the lightest area, we can observe about 0.5 to 1 meter inundation difference in this extreme hurricane Irene event.
This is about your validation results. Are they generally depending on some kind of a specific event for the Connecticut River? And what will be the advantage of using your model? I'm assuming that this is for the CREST model it's referred to, compared to the other NOAA models for the riverine flow.
I think they ask about the depth, right? If the depth, this is about the CREST plus HEC-RAS model. If they ask about discharge, then it's about the CREST model only. So I want to make sure, is this map the question about?
Yes, this is about this is the questions about mostly the why would they choose the CREST model like to use instead of like just the riverine flow from the USGS gauges or other NOAA models?
Oh, okay, thank you. So first of all, if we just use the USGS observation, you can have certain time series over some rivers, but you cannot get it everywhere. So that's the main functionality of a model. If you have a model for any river, you can output a result, right? So the basic idea is to use USGS observation to calibrate our hydrological model and then apply it everywhere after it's verified. Another thing is that, so another question might be why we want to use CREST again versus other hydrological models. Because CREST has a high, is designed for running at high spatial temporal resolution, as I showed, which can be hourly, and 500-meter resolution for the runoff generation, and 30-meter for the discharge generation, which is higher than most of the models, especially those models who consider the physics of the snow accumulation and melting process, which is very computationally intensive. So because CREST used the parallel and vectorization computation, so it can solve those processes, those balances very fast. So that is why it's successfully applied to the high latitude regions like the Connecticut state.
Mm-hmm. This is about the New Haven case again, because you showed the cases with just the river, like the base flow versus like the compound flooding.
Yes.
In that results, like, are you saying that the base flow or the river flow addition to the flooding is around like 0.5 to 3 meter range of flood depth?
In some urban area, it can be, yes, according to the model.
Mm-hmm.
Like this region.
Mm-hmm. And one last question.
Yeah.
Sorry, go ahead.
I mean, because this region is both close to a river, to a main river, and to the coast. So this could be the most severe area that's impacted by the compound flood.
And finally, what are your suggestions for the riverine communities to prepare for higher precipitation events?
The riverine, you mean the mitigation procedure? Is that?
Yes, for the inundation procedure, yes.
For the riverine flooding, my suggestion, there are several folders. So there are definitely some engineering approach, like to build some levees and so on. There are also some green solutions. I just read some articles from literature. It could be like, for example, you can restore more green, more wetlands, which could serve as a sponge. If there's a heavy precipitation, then it can absorb some of the water and some of the faster flow, and then release it slowly, so it can reduce the flood peak. During a drought, it can also slowly release some preserved water, so you can actually both reduce the impact of flooding and drought. So that's the green solution. I think I recommend a little more on the green solution.
Thank you so much. This seems like all of the questions so far. And thank you so much for attendees for joining us today. Just a reminder to you, for our next presentation is going to be on Wednesday. And we are going to, if you want to learn more about Dr. Shen's presentation, there is actually a fact sheet prepared for this. You can come to our website and go under his presentation. You can see the fact sheet, and we'll upload the video of this webinar soon on our YouTube channel. So the next presentation this Wednesday is going to be from Dr. Yan Jia. He's going to talk about simulation and momentum analysis of the tides over the salt marsh at Guilford, Connecticut. We hope to see you on Wednesday. Thank you so much for attending.
Thank you.